Welcome back to the course in Nuclear Medicine Physics. Today, we'll be looking at nuclides. Specifically, we'll look at the binding energy of different configurations of protons and neutrons. This is the energy required to assemble all these individual particles together into a nucleus. This energy is important because it tells us when a radioactive atom decays, how much energy is released. If you enjoy this lecture series, please be sure to like and subscribe. There'll be plenty of interesting videos in the future. Anyways, enjoy this video.
So we finished the last lecture talking a little bit about that chart of nuclides. We talked about how do we represent a nuclide. We talked about isotopes, isotones, isobars. We saw that we can plot all the nuclides that we know in this type of chart, and we know about 3,000 of them. And we see that this dark region here in the middle is what we call the line of stability. It means that those are the nuclides that have a very, very long life. They will exist in nature for a very long time in that particular configuration. And what we're going to see today is how there are processes that take these different nuclides and bring them closer to this line of stability. And that's basically what happens in radioactive decay. So just to test a little bit of the concept, really quick, let's see if you guys can identify from which of these following options, which ones are isotopes.
Answers are coming in, so please enter your answers. We have had about half of you enter them so far. Again, these polls are anonymous, and just feel free to share with us what you think is the answer, even if you're not really sure.
Okay. And I'm going to stop it in 3 seconds. Most answers have been arriving. Okay. So yeah, so most of you are right. So yes, is the lutetium element that has different isotopes. Remember, an isotope always has the same proton number. It's just the neutron number that changes. So that's why the total mass changes here. And the reason I brought this is because from now on, we're going to talk a lot about isotopes. So all the time in the course, we're just going to be referring to radioisotopes. And lutetium-177 is just a very common. Lutetium in particular is, we like some of those isotopes of that element. Okay, we talked a little bit about why there were more neutrons than protons. That's how we talked about the different 4 fundamental forces in nature. And I mentioned a little bit about the Standard Model. And we saw that is the strong force that is holding these nuclides together in the nucleus. Because there's a Coulomb repulsion effect because of the charges, they're going to be repelling from each other, but the strong force is stronger than that electromagnetic force, so it can keep the nuclides together. Now, well, this has an effect, and is that the size of the atoms, when you look at atoms, and is what you see here, if you look at the size of the atoms, which is the y-axis, and we're looking at that as a function of the proton number of the nuclide, we see that atoms, like the size doesn't really change, like following like a particular pattern with Z. It just like goes random, and then when we fill a shell, it has big jumps. But when you look at the nucleus has like a nice steady growth. And the nuclear radius is typically given by an equation that looks like this. It has a constant, and that constant depends on the model that is used to measure it. But there's a model that is called the charge distribution. If you account for that, then from that model, we have a constant that is 1.07 to 10 to the minus 15 meters. But the reason I'm showing this is because this goes to the 8 to the 1/3, and if you think about density, and density is mass divided by volume, and if you think about the nucleus as being a sphere, then that has to go to the R cube. So when you do this R cube, you basically end up with A, and the mass is related to A. So A over A will cancel out. What this has an effect on the nucleus is that the nuclear density, so the density of the nucleus that we know, is pretty much constant. Well, it is constant. The effect of A cancels out. So keep that in mind when we talk about nucleus, and we'll see why that has an effect in a moment. So there's these nuclear binding energies. In the previous lecture, we talked a little bit about the binding energies of the electrons to the atom as a whole. Now we're starting to look at the nucleus itself. So when you look at the nucleus, it turns out that there's also some binding energies. And what's going on there is, if you sum the masses of the different constituents of the nucleus, that is always going to be greater than the mass of the nucleus itself. So that difference in mass, and all this comes because of this equation that is very famous from Albert Einstein, E equals mc squared. And what this is basically telling us is that energy can be converted to mass, and mass can be converted to energy. So it's because we see that difference in mass of the different constituents versus the total nucleus as a whole. We know that there's some energy, some of that mass got converted into energy, and that's energy is what's holding that nucleus together. And what I mean by constituents is the neutrons and protons in that nucleus. Yeah, so to put a little bit of equation, so what I'm saying is, okay, if you take the mass of the nucleus, let's say we have a mass of a nucleus formed by Z protons and N neutrons, that is smaller than if you add the sum of Z protons plus N neutrons. And we can then define the binding energy as the difference between the sum of the different constituents minus the mass of the nucleus as a whole. And we're defining it like this, and we're defining it to be greater than 0. We know that the nucleus form is always going to be smaller than the different constituents. So, I mean, if you want to think about the binding energy from another point of view, is what is the energy that is needed to separate all the nucleus from that nucleus? If you want to take the nucleus and take each particle apart, you would need all that energy to put it apart. Or if we wanted to assemble a nucleus with Z protons and N neutrons that are initially separated from each other by an infinite distance, then the binding energy is the amount of energy that is released when you assemble that nucleus. So I have a question. May atomic size has a role in nuclear medicine, imaging, or therapy? Okay, let me get to that a little bit later. So back to the binding energy of electrons around the atom, we can define the binding energy of the electron in this way. So if you have Z particles in the nucleus and you have the mass of the nucleus, then you can define the binding energy like this, and it's again greater than 0. So how is the nuclear binding energy determined? How do we know the mass of the nucleus? This is what we want to know. It turns out that they are measured from masses of atoms, as those are much better determined than nuclear masses. So it's not very easy to measure the mass of a nucleus, but it's easy to measure the mass of an atom. And there are methods for that, like, for example, mass spectroscopy would help for that. So what we can do is we can write the binding energy using the previous equations, and I encourage you to look at this in more detail when we're done, when you have the slides at home. The binding energy of the nucleus, we can write it in terms of the mass of the atom by combining this equation and the equation that I had back here. And this is commonly better represented in terms of the hydrogen atom. So if you think about the hydrogen atom, the mass of the hydrogen atom, C squared, would be the mass of the electron plus the mass of the proton minus the binding energy of that electron to the hydrogen atom. And which is what I have here. And you think we can multiply this equation by Z on each side. And from this last term, we can assume it's more or less a good approximation that Z times the binding energy of one electron, which will be what we see in the hydrogen atom, is approximately the binding energy of the electron when you have Z protons in the nucleus. So then we can have an equation for binding energy that it shows like, okay, we have Z times the mass of the hydrogen atom plus the number of neutrons plus the mass of a neutron minus the mass of the atom, all that multiplied by C squared, because we're talking about energies. And you're encouraged to check how we follow the process to get here. Then there's a way of defining binding energy. So typically, atomic and nuclear masses are often given in what is called the unified mass units, and it's represented by a U. So what this unit stands is basically is defined as 1/12 of the mass of a neutral carbon-12 atom. And the rest energy of one unified mass unit is related as well. One unified unit times C squared is equal to 931.5 MeV. So yeah, so as I said earlier, masses of atoms are easily and accurately measured in a mass spectrometer. So, okay, let's think a little bit then, to summarize what I just said, let's think about this problem. So if you have the mass of a helium-4 atom, and is this value of unified units, and you have the mass of a hydrogen atom, and the mass of the neutron, how much is the mass deficit, the difference in mass between the atom and the sum of the masses of independent constituents for the hydrogen atom? Let's see if you guys can think about that for a couple of minutes. So again, think about as the mass of the constituents and compare that to the mass of the atom as a whole. Let you guys think for a moment.
I'm sure some people are pulling out their calculators here.
Yeah, that's fine.
So for those watching this recording, you could try to do that too, while we await those listening directly to do this.
So again, so what we're trying to see is, we know that when we have a nucleus as a whole, an atom as a whole, the mass we always see is smaller than if we had the different constituents of that atom, of that nucleus, separate. Okay, let's wait 30 more seconds and we'll talk about it. Someone is asking me, how is that 1 squared equals 931.5 MeV relevant to the question? It might or it might not be. We'll get there in a moment, but it's just, I just wanted to put it there so that, because we're talking about use here, so that you know how U relates to energy. Okay, let's end the polling now, and I'll share the results. So you see that the results are mixed, although, yeah, most of the people had the correct answer. The correct answer is C. And well, just to clarify, let me make this work. So we're trying to do.
Carlos, your face has been lowered.
Yeah, sorry, it's been lowered because I'm
Okay.
gonna write on my screen.
Yeah, it's fine.
So, well, basically we're doing the. Oh God. So I'm having a technical problem. Yeah, so it's basically 4.002603 U, which is the mass of the 4 helium atom, minus we have 2 of the hydrogen 1 atoms plus 2 of the 2 neutrons. So, well, basically, if you plug in the values there, that should give you the value for C. Are there any questions about this? Or is it more or less clear? Okay, let me know in the chat, but.
Because the hydrogen one atom is a proton. So basically you have 2 protons and then 2 neutrons, and you're subtracting these. And one of the people in the chat asked about the importance of that equation. In this case, that C squared doesn't matter. That's just there to, I guess, to trick you.
Yeah, and then I encourage to go back, but keep in mind what we're doing here is we're actually using the hydrogen atom. So we're using the proton plus the electron. So the masses of the electrons are accounted for here. So think about it between now and Tuesday, and we can discuss more on Tuesday, but when you go and look at the equation that I posted a moment ago. But the reason that is there, and it's because I have another poll. So let's see if we can find, okay, we already calculated the mass deficit for that nucleus. What is the binding energy then? And okay, 2 answers. Some people are putting numbers. I'm not gonna spend too much time here. Okay, 5 more seconds. I know there's people still missing, but I wanna move forward. It's gonna end the poll, the results. So yeah, so the answer is C. So that's why I had that equation there in the positive phase of destruction, but you needed it here. Yeah, if you multiply this by 931.5 MeVs, you end up with 28.30 MeVs. So that is basically an alpha particle. We're gonna talk about that in a moment, but that's the binding energy. So imagine now that we take many nuclides and we plot this in, well, the mass number on the horizontal axis and the binding energy on the vertical axis. But see here that I have this plot as binding energy per nucleon. So for example, if we look at what we just calculated, the binding energy of the helium-4 nuclei, we just saw that it was 28.3. But when we do per nucleon, because we have 4 nucleons there, that gives me a 7.07 MeV per nucleon. So this is for the nucleus. As a reference, the binding energy of an electron in the ground state of hydrogen, like the binding energy of that electron to the hydrogen atom, is 13.6 electron volts. So look how when we talk about nucleus, we have an order of MeVs, mega electron volts, and in the case of the hydrogen atom is measured in electron volts. So we see that that binding energy in the nucleus is much, much bigger than when we talk about electrons bounded to the atom. And look at this hydrogen-3 and helium-3. We see that they have slightly different binding energies, but they still have 3 nucleons. So, I mean, if anyone can maybe type in the chat, what do you guys think the binding energies of those A = 3 nuclei are slightly different? We still have 3. Anyone wants to maybe type an idea or say it out loud? Okay, so think here we have, what we have in the hydrogen-3 is 1 proton and 2 neutrons. Yes, exactly. And there's a different neutron count, and here we have 2 protons and 1 neutron. So what's causing that difference in binding energy is here you have a strong force, nuclear force, but here you have now 2 charges repelling each other. So that's reducing that binding energy, because now there's this electromagnetic force trying to split them apart. That's why helium-3 has a lower binding energy. Okay, but there's something interesting about this plot. And if you see, okay, as we start going up, we see that at some point this doesn't keep growing up. This is more or less roughly constant at somewhere around between 8 to 8.5 MeV. And this is due to the saturation of nuclear forces. So what I mean with this is, remember how the strong force only has a very short range of interaction? So what this is showing is that each nucleon in that nucleus interacts only with its neighboring nucleons. So if you have, I don't know, a very big nucleus of many neutrons and protons, not every proton, not every neutron will interact with every other proton or every other neutron in that nucleus. It's just gonna interact, it only interacts with the neighbors. And because of that interaction only with the neighbors, because of the limited range of the strong force, is that this plot stays mostly constant. Well, this curve has a maximum around A = 56. Well, no, at 8 = 56, which is for iron. And this fact is very important in the synthesis of elements and nuclear power production. So I want you guys to think, look at that plot, and think about how much energy is going to be released when producing a helium-4 nuclei with 2 deuterons. So 2 deuterons is 1 proton and 1 neutron, a hydrogen atom. So try to think on that graph and see if you can answer this question. So let's see, so the 4 hydrogen is around, so the helium-4 is around here. I don't know if you see my 4 helium is here, and the deuteron is here. So somehow we're moving from here to there. Okay, I'm gonna end the poll for now. Let's share the results. We have a tie between B and D. Well, this is the correct answer. So let's see what's happening. So then, okay, so if we look at deuteron plus deuteron, we see that we have 2 MeV for each. So again, remember, this is the binding energy per nucleon. So here we have around 1 MeV, but we have 2 nucleons. That's why we have 2. And we're combining 2 of those. So we have 2 plus 2 for, well, for the hydrogen atoms. But when we get to the helium-4, which is up here, we have more or less 7 times 4 nucleons, that's 28. So the energy that's released is the difference between now this 28 binding energy minus that 4 binding energy. This released 24 MeVs. So the correct answer was D. Minus 24 MeV, I guess, which is the other answer, that would mean that you would have had to put 24 MeV into the system to be able to have that final atom. So if it's released, because of the way we're defining it, is positive. So going from down here to up here means that energy is released. And this process is what we call fusion. So basically you are taking smaller nucleus, combining them together into a bigger nucleus, and well, as long as, and that releases some energy. So let's see now, in a similar procedure, you saw what we just did. So how much energy per nucleon is released if we try to fuse 2 iron 56 nuclei? So that means if you are combining 2 iron 56, you're gonna end up with a big nucleus of 102, A equals 102. Sorry, 112.
Difficult questions.
Yeah, I just want you guys to start thinking and see if you are able to start interpreting these. I know, well, we're working together on it, but that's why I want you to think before I show you the answers. So we're going from, look at it this way, you're going from around here to somewhere around down here. Okay, so I'm gonna end the poll there. I'm gonna share the results. Most people are saying C. So most people are saying that there's 10 MeV per nucleon that are getting released. Okay, let's look. So the maximum is at this curve. So we're gonna say, okay, that's more or less around 9 MeV per nucleon. If we're gonna combine 2 of those, that's gonna give us 18 MeV per nucleon. But then that's gonna bring us down to somewhere around 112, which is gonna be more like 8 MeV per nucleon. So you started with 18, you end up with 8. So 8 minus 18, that would be minus 10. So the correct answer was D. But there's a problem with that. And if it's minus 10, that means that there was no energy released. What that means is if you want this to actually happen, you would have had to put 10 MeV per nucleon to be able to get that. So this needs energy. So only nuclides up to A equals 56 can be formed by fusion. So yeah, we cannot keep going because that will require energy. So let's think it the other way around then. Let's take a heavy nuclide like uranium-235 and assume that it's split in 2 equal parts. So uranium-235 is going to be somewhere around here. So split it in 2 equal parts and see how much you think the energy release is going to be.
Again, don't worry if you're not able to really even fully understand what's going on here. You're gonna learn. These are tough questions you're being asked right now, so hang in there.
Okay, 10 seconds. Okay, let me show the results. So most people say A. So yeah, A is the correct answer. It's good to see as we went going through these questions, more and more people started getting the correct answer. So that's a good sign. But let's look at why is that happening there. So let's say we have uranium-235. So we split it in 2 equal parts is more or less, I don't know, around 117. You're going to be somewhere around here. So you're going from down here to from around 7.5 MeV per nucleon to having 2 parts of around 8.3 MeV per nucleon. So that would be a total of 16.6. So you end up with 16.6 MeV per nucleon as a binding energy. You start with 7.5, and the difference between those two is around 9 MeV per nucleon. And this process of from going from when you have a heavy nuclide and you split it in different parts, and that releases energy, that's what is known as fission. So again, look at this plot. Because of this plot, we know that if we want to release energy with light nuclei, we need to combine them together, we need to fuse them. If we want to release energy with heavy nuclei, we need to split them apart. And what's happening on the left is actually what stars do. Stars are basically fusing elements, and that's how many of those elements, that's how elements in the universe gets formed, and then the splitting apart also follows. So if a nucleus is stable, energy must be provided to break it up. So again, when we're talking about that line of stability and that some nucleus just disintegrate into some others, is because they're spontaneous changing those configurations that don't require energy to be input into the system. But if a nucleus is stable, that means it's going to be like that in nature for a very, very long time. If we want to break it up, we need to add some energy. And again, we saw that and we saw those equations. So take a look at that. Now, when we think about nucleus, remember when we talk about the electrons around the atom, we talk about the different shells of the atom, and we talk about the K, L, M, N shells. Well, it turns out that nuclei also show a shell structure, like the atoms. We also have different shells. And experiments show local maximum of the binding energy for some nucleons. And these nucleons are very, very well-bound systems. So for example, if you start looking here down from the bottom, we see, well, there's kind of a maximum here at helium-4. There's another little maximum here at C12. There's another little maximum here at O16. And those maximums, those local maximums, occur at what is known as magic numbers. So it occurs, there are some magic numbers for protons and magic numbers for neutrons. And the reason that they end up showing those higher binding energies is because they form complete shells. And some examples of magic numbers that you'll find is 2A20, well, there's this 126. This last one only apply for neutrons. But these nuclei, the magic number nuclei, are very, very stable. And just for completeness, I wanted to show you guys the elements abundance in the universe. So if you take a look at basically all the elements that we have in the universe, hydrogen basically composes around 71% of the atoms of the elements out there. Helium is about 27%, and then all the other elements summed up is about 2%. So let's come back to the chart of nucleus. Now we know about these binding energies, and now we know that only few nuclei are stable. We know about 3,000 of them, but most of them decay in different ways.